Question 3 reads as follows. A 600 Newton force is applied at an angle of 60 degrees to the horizontal. So let's say we have an object here. Now the question goes to say the object has a mass of 80 kg and moves to the left along a linear frictionless road. So this means this force has to be applied in this direction for the object to move to the left. Okay, what's happening here? Alright. This means the force F is applied. They say here is applied at an angle of 60 degrees to the horizontal. Remember that this line here is the horizontal. So the angle would be here at 60 degrees, right, to the horizontal. So this is 60 degrees. And we're saying this object has a mass of 80 kg. It moves on a frictionless horizontal surface. So this means that there is no friction between the two surfaces. Now, the other thing that I'll do quickly is that I'll choose direction. I'll choose my direction using the reference frame to say anything that goes in this direction is positive and anything that goes in that direction is also positive. Now, the other thing to look at here is that we write our given data to say the force F that is being applied is 600 Newton and the angle theta is 60 degrees at which this force is applied, and the mass of this object is 80 kg and there is no friction here. The friction is 0. If you have been paying attention, you would see that I was interpreting this question, right? I was doing the interpretation. Now, I will then look at this question and say, from what I've gathered here, this question would use Newton's laws of motions, particularly Newton's second law, and it might require us to know a little bit about the different types of forces, like your normal force. That could be something that should be coming into your mind, right? So that means I've classified this question to say which part of the theory does this question fall under. I've classified that question C, right? Now I'm ready to answer this question because I have a little bit of an understanding as to what is happening in this problem and what is the expectations, what theories are there. So 3.1, they say draw a free body diagram for the object. I'll draw a dot there to represent the object, and I would say the force that exists here is the normal force. So this is the force that the surface exerts on the object in the vertical direction and making an angle of 90 degrees. We also have the force of gravity, which I'll write as mg here. We then also have a force that is applied in this direction because the object moves to the left, right? So this is the force F. Now, this force, if you look at it, is sitting between the y-axis and the x-axis. It's in between the two axes. So this is the x, this is the y. this force is in between these two axes, it means it must have components. It must have a component, meaning a force that goes in that direction, and a force that goes in that direction, the x component and the y component. So what I'm saying is that another way of looking at this problem is saying if we pull this object by a force that goes in that direction, the y direction, and another force that goes in that direction, it will move in the same way as when we pull it with this force here. Right, these two forces in the x and in the y, they make up this force. It becomes the resultant. And you would know from our lessons when we broke down forces into components, and I was explaining how we come about into components, you would notice that this force here can be written as, so this will be the fx, and here it will be the fy. Actually, I'll move it to this direction. This side here, it will be your fy, and the angle here will be the 60. So it will make a 90-degree angle here. So we have a right angle triangle here. So you can use your trig ratios to solve this problem. Right? Now I will jump into question 3.2. Right? I'll jump into question 3.2 where they say calculate the acceleration of the box. Right? So this will be a problem that and just to come back here quickly and write this here. The A stands for the answer. We are answering the question now because we have interpreted and classified the question, right? Now, here we continue to answering it through a calculation problem now, where we then come and say this will require us to use Newton's second law, where we say the net force is equals to the mass times the acceleration. So we are looking at the acceleration that the object has as it moves in this direction, right? So that's the acceleration we're looking at here, and the net force is the net force of all the forces that are acting in the x direction, in this direction here, right? Because they're the ones that cause this acceleration. Now from our free body diagram, you can see that the force that acts in the x component is this force fx, right, which will be given by f cos of theta, right, or cos of 60. Why? Because in this right angle triangle, you will say the adjacent side over the hypotenuse f. Remember, this side here is f, and then that should give you fx is equals to f cos theta, right? Now, to understand how I came to this point, please go to the previous lessons. I have different cases where I break down how to get to this formula. Now, in this case, it means when I add my forces, I will have the force in the x, which is given by the negative f cos theta. It's very important to understand why I'm using a negative here. We chose at the top here that anything that goes to the right is positive, and anything that goes to the left has to be negative. And our force from our force diagram here, it's going to the left. Even here, when we throw, you can see it there. So that's why it's going to be negative. You also have to note that there are no any other forces. It is this only one force that has this component here in the x that is applying the force. So it is the net force, because you can't add any other forces. There is no friction, right, or even any other forces in the horizontal. So this will be equals to ma. Now I'll substitute at this stage so that I have 600 here, the cos of 60, because our angle is 60 degrees and the mass is 80 kg, so we'll have 80a. Now at this stage, I will divide both sides by 80 so that I'm only left with the A, because the 80 and 80 will cancel on the right hand side, so I'll be left with A is equals to, now I can punch this whole thing in my calculator to say I have 600 times the cos of 60 divided by 80, and then this would give me the negative 3.75 meters per second squared. Now, very important, don't forget this negative here, right? So this negative will tell us that the acceleration is actually going to the left, because it is negative to the left. Yes, because it's negative. Remember, right is positive. In fact, already I'm thinking about my answer. As you can see, I'm already navigating the answer. I'm already here on navigation, right? Trying to see if this answer makes sense. Well, it does make sense, just, from the argument of direction. I'm expecting my acceleration, even on our diagram, we've drawn it to be going to the left, because this box is actually moving to the left, since our force is directed in that direction, and there's no friction. The other thing is that this acceleration is a bit high. It's almost 4 meters per second if you look at it. I mean, it's because there's no friction, is a bit high. If there was friction, it will reduce a little bit, because we would have added here friction. So it looks roundabout right. The other way in which you can navigate this problem really is to change some of these parameters. What you can do is that you can swap your direction here, and do it the other way around. Say this is positive and this is positive, and look at how the answer should change. We expect to get the same value if you change direction, right? But you still have to get the answer that says we're going to the left, even though the direction has changed. I mean, that will ensure our answer is still correct. The other thing is that you can change the mass, make it small or big, and see how the acceleration changes. Obviously, a bigger object wouldn't have a high acceleration, and a small object will have a high acceleration. If that doesn't happen when you change your values, it means this answer, there's something wrong. We might have done something wrong. You can even play around with this force, to change the angle here, and see how it affects the acceleration. So you can increase the angle so that, your force is sitting like that, you have a smaller angle here, or you can make it like this, or you have a bigger angle here, until also you come to the horizontal, and check how this acceleration would change. I mean, the more you bring your force here, the more the acceleration should go higher. And if you sort of bring the acceleration here, the object won't move horizontally anymore, because you are now getting to a point where you're pulling it up. You expect to have a zero acceleration in this direction and starting to have an acceleration in the y.